Good day, sir. Good day, everyone. So, I am Maria Isabel M. Mallorca. I am a third-year student from BS Ed Mathematics program at the University of Southeastern Philippines, Tagum, Mabini campus. So, I am tasked to tell you more about the infinite series on positive terms. So what is that called? So it is a sequence of numbers arranged such that each term in the sequence is positive and the sum of these terms extend indefinitely. So understanding this series is crucial. Why? Because they form the foundation for advanced mathematical analysis, particularly if we want to determine the convergence or divergence of the given series. So, we all know that convergence refers to where the sum of the series approaches to finite value or infinite value as the number of term increases. So, while the divergence occurs when the sum grows without a bound. So, in exploring infinite series with positive terms, we utilize various tests such as the comparison test, limit comparison test, and the integral test. So we will discuss this various tests to determine whether the series converge or diverge. So the comparison test compares a given series to a non-convergent or divergent series, while the limit comparison test involves taking the limit of the ratio between the terms of two series. And lastly, the integral test represents the terms of a series by integrating the function. This test allows us to determine the convergence and the divergence of a series without finding the exact sum. So what will be our objectives for today? So we all have three objectives. Use the comparison test to check if a series converges or diverges by comparing it to a known series. Another, apply the limit comparison test by finding the limit of two series term ratios to decide if they converge or diverge. And lastly, use the integral test by integrating a function to determine whether a series converges or diverges. So firstly, we will talk about what is a comparison test. So, in comparison test is that the idea is we're going to compare a given series with a series that is known to be convergent or divergent. For instance, we have the summation of 1 all over 2 raised to the power of n plus 1 ranges from 1 to positive infinity. Is almost the same to what? It is the summation of 1 over 2 raised to the power of n ranges from 1 to infinity. This is the summation of it, which is an example, really, as you can see here, that it is an example of geometric series in which the first term or the a that we have here is 1/2, and the r, or the ratio, as you can see here, the 1 over 2 raised to the power of n is we can find that the r is 1/2. So by theorem of geometric series with r, or the absolute value of our ratio less than 1, we can determine if it is convergent. Since our r here, the absolute value of r, which is the absolute value of 1/2, is less than 1, therefore we can conclude that the series 1 over 2 raised to the power of n, the summation of it from n equals to 1 to positive infinity, is therefore convergent. Because the series the summation of 1 over 2 raised to the power of n plus 1 ranges from 1 to infinity is so similar to the geometric convergence series that we have, which is the summation of 1 over 2 raised to the power of n ranges from 1 to infinity, the summation of it. So we have the feeling that this series, or the given series that we have here, must must be convergent. Indeed, it is. Let us find out why. No? Let's try to compare the two. Let's have the inequality. So the inequality of 1 all over 2 raised to the power of n plus 1 is less than 1 over 2 raised to the power of n. Shows that our given series the summation of 1 over 2 raised to the power of n plus 1 ranges from 1 to infinity has smaller terms than those of the geometric series. And therefore, all its portion sums are also smaller than 1, the sum of the geometric series, right? So, similar reasoning can be used to prove the following test, which applies only to series whose positive terms, meaning that this comparison test can be applied to infinite series of positive terms. So this part says that if we have a series who's smaller than those to be known convergent, then our series is also convergent. So we have a series, and we have the series that is known to be convergent. If this known to be convergent series is greater than our given series, or the given series is smaller than our convergent known series, so we can by comparing them, the terms of the given series with those of known convergent series. So this comparison test is proven or supported by the theorem of it. Now, so this procedure is a particular case following the theorem known as the comparison test. So what it tells us about this? So the comparison tells us that suppose that we have the summation of u sub n ranges from 1 to positive infinity be a series of positive terms. So the condition number 1, so if this series of positive terms is convergent, it can be proven by the condition number 1, which tells us about if the summation of the Vn ranges from 1 to positive infinity of positive terms known to be convergent, and then the u sub n, or our given series of positive terms, is less than 2 dot series that is known to be convergent from all positive terms n, then also we can conclude that the summation of u sub n ranges from 1 to positive infinity is also convergent. Second condition, what about if it is divergent? So we have this second condition. The second condition tells us if we have the summation of v sub n ranges from 1 to positive infinity is a series of positive terms known to be divergent, and u sub n is greater than v sub n for all positive integers n, then the summation of u sub n ranges from 1 to positive infinity is also divergent. So let us have an example for this one. So we are going to determine whether the series converges or diverges by applying the comparison test that we talked about earlier. So we have the summation of 5 over 2n squared plus 4n plus 3 ranges from 1 to infinity. So for this one, for the solution, firstly we have to indicate that we are going to apply the comparison test. So for large n, the dominant term in the denominator is 2n squared. So that means that we have to compare the series with that dominant term in the denominator. Yeah, dominant term in the denominator, which is the 2n squared. So it will be the series v sub n that we were going to have is the summation of 5 over 2n squared ranges from 1 to positive infinity. As for that, we're going to let the u sub n equals to 5 over 2n squared plus 4n plus 3, and v sub n equal to 5 over 2n squared. So observe that we're going now to compare the two series, the u sub n and v sub n. So u sub n, let's try to prove if that u sub n is less than or equal to v sub n. So we have the u sub n, which is the 5 over 2n squared plus 4n plus 3 is less than or equal to 5 over 2n squared. So for this one, we're going to try to write the first two terms to help us compare the two series, right? So we have the first term for the given series is 5/9 and 5/19. So for the next term, we have the 5/2 and 5/8. So for this one, by listing the first two terms of the series, which is for the summation of 5 over 2n squared plus 4n plus 3, ranges from 1 to infinity, and the summation of 5 over 2n squared ranges from 1 to positive infinity, we've noticed that the elements from these two series is that 5 over 9 and 5 over 19th is actually lesser than the v sub n that we have, which is the 5/2, which is the 5/2 over 5/2, and also 5 over 8, 5/8. So therefore we found out really that our u sub n is lesser than v sub n. So it means that our the summation of 5 over 2n squared plus 4n plus 3 ranges from 1 to infinity is lesser than the summation of the series of 5 over 2n squared ranges from 1 to positive infinity, because the left side, as you can see here, that the left side has a bigger denominator. So as you can see here, we've proven the limit comparison test, which is the first condition in which the u sub n must be lesser than the v sub n, and the v sub n must be known to be a convergent series. So for this example, we found out that the summation of 5 over 2n squared plus 4n plus 3, the summation of it ranges from 1 to infinity, is a convergent series using the comparison test. So let us proceed with example number 2. So for this one, we're going to determine whether the series converges or diverges. So our given series is the summation of natural log of n plus 2 all over 2n, rather, ranges from 1 to positive infinity. So for this one, now we must apply or indicate again the comparison that the test rather that we're going to apply, which is the comparison test. So we have to find the v sub n. So for finding the v sub n, we have to determine the dominant term in the denominator. So as you can see here, we have n. So we should compare it to the given series, and our series v sub n would be equal to the summation of 1 over n ranges from 1 to positive infinity. So now we have the u sub n and v sub n. We are going to let u sub n be equal to the natural log of n plus 2 all over n, and b sub n is equals to 1 over n. So we can observe that the u sub n should be greater than or equal to v sub n. So we have, what is our u sub n and v sub n? So we have the ln of n plus 2 over n, which should be greater than or equal to 1 over n. So for this one, we have to apply what we did earlier. We have to list the terms, the first two terms at least, to compare the two series if it is less than or equal or greater than or equal. So for the natural log of n plus 2 over n, we have the ln or natural log of 3 and the natural log of 4 halves, which is approximately equal, to really compare them now, approximately equal to 1.0986 and 0.6932. And ln and 1 over n rather equals to 1 and 1/2. So by this one, we know that the summation of 1 over n ranges from 1 to positive infinity is a harmonic series. So we already know that a harmonic series of a positive terms is a divergent series. So since the summation of 1 over n ranges from 1 to positive infinity of a positive terms known to be convergent, and we really prove that u sub n is greater than v sub n, in which our u sub n is ln of n plus 2 over n and the 1 over n. So the ln n plus 2 over n is greater than the 1 over n by just simply listing it, no? So for all positive terms of n. So therefore the series such that the summation of the lateral log of n plus 2 over n ranges from 1 to positive infinity is divergent by part 2 of the comparison test. So this part 2 tells us if the u sub n, or the summation of u sub n, ranges from ranges from positive 1 to positive infinity. Now, it's a series of positive terms na with divergent. So we have the v sub n earlier, which is 1 over n is a divergent series, is a harmonic divergent series. And we prove also that u sub n, which is the ln of n plus 1 over n, is actually greater than 1 over n. So for all positives of n, then we really can prove or conclude that our series, no, is a convergent series. So I hope you understand the topic well. So we can now proceed to the next test. We have already talked about the comparison test, and now we're going to talk about the limit comparison test. So the limit comparison test is the ratios of two series. We're going to find the limit of the ratios of the two series. So what is that all about? When can we apply this limit comparison test? No? So for this one, let's try to look at the series, which is the summation of 1 over 2n squared minus 1. So earlier, the example is about, for the comparison test, is that the summation of 1 over n squared plus 1, as you can remember, ranges from 1 to infinity. So for this one, we have the negative 1 at the denominator instead of positive 1. So the terms of this series must be smaller than those of the convergent series or larger than those of divergent series. So then the comparison test does not apply. So let us consider this for an instant. The series of the summation of 1 over 2n squared minus 1 ranges from 1 to infinity. So let us try to apply the comparison test. So 1 over 2n squared minus 1 is greater than or equal to 1 over 2n squared. 2n squared is useless as far as the comparison test is concerned, since u sub n must be lesser than or equal to the v sub n to be considered before applying the theorem of the comparison test. In such cases, for this one, we can now use the limit comparison test. So what the limit comparison tells us? The limit comparison tells us, the ratio, finding the limit of the ratios of two series. So in the limit comparison test, which follows, or like below of it, so it's a sequence of the comparison test and it's often easier to apply. So this is the theorem on the limit comparison test. Let's talk about the limit. So for this one, we have three conditions. So suppose that we have the summation of u sub n ranges from 1 to positive infinity, and the summation of u sub n ranges from 1 to positive infinity are series with positive terms if the first condition that we have is that the limit of u sub n over v sub n as n approaches to positive infinity, and it is equal to c that is greater than 0, which is like 1, 2, 3, 4, then the two series either both converge or diverge. We have the second condition. The second condition tells us that the limit of u sub n over v sub n ranges from positive infinity is equal to 0, and if the summation of the v sub n ranges from 1 to positive infinity converges, then the summation of u sub n ranges from 1 to positive infinity also converges. That is for the second condition only if the ratio of the limit of the ratios equals to 0. Then the condition number 3 here, we have the limit of u sub n over v sub n as n approaches to positive infinity is equal to positive infinity. So, and if that's the case, we have the summation of v sub n ranges from 1 to positive infinity diverges, then our summation of u sub n ranges from 1 to positive infinity also diverges. To furtherly understand what this limit comparison tells us, let us have an example. We will have two examples, so let's have examples. So let's try to test the series for convergence or divergence, but now we were just going to apply the limit comparison test. As you can see here, this series is given earlier, so we cannot apply the comparison test rather. So we should apply the limit comparison test, which is the limit of the ratios of the series. So we have the summation of 1 over 2n squared minus 1 ranges from 1 to positive infinity. So for this one, solution, we're going to apply the comparison test first. Then let our u sub n be equal to 1 over 2n squared minus 1, and v sub n equals to 1 over n squared. So we still consider the dominant n in the denominator. So we have the 1 over n squared now. So for this one, we apply the limit of u sub n over v sub n. So we have now the limit as n approaches to positive infinity of 1 over 2n squared minus 1 all over 1 over 2n squared. So for this one, we have to multiply our numerator by the reciprocal of our denominator. What's the reciprocal of 1 over n squared? It is n squared over 1. So we need to multiply them. So the limit of 1 over 2n squared minus 1 multiplied to n squared over 1 as n approaches to positive infinity. The next thing we do is to multiply the numerator to numerator and denominator by denominator. So what we're going to have now is the limit of n squared over 2n squared minus 1 ranges from positive infinity. So for this one, we have to multiply both numerator and denominator to the 1 over n squared, in which the n squared is the highest highest exponent of a variable in the denominator. So for this one, we have now the limit of n squared over n squared all over the n squared over 2n squared over 2n squared minus 1 over n squared rather, as n approaches to positive infinity. As you can see here, we can have an answer of 1 from the numerator and 1 for the denominator multiplied to 2, and then we have a 2. So let's try to look at it. So it is the limit of the limit of n over 2 minus 1 over n squared as n approaches to positive infinity. Right after that, we can apply now our limit, which is n approaches to positive infinity. It now became the 1 over 2 minus 1 over infinity squared. So infinity squared is simply infinity, and 1 over infinity is what? It is 0. So we have now 1 over 2 minus 0 equals to 1 half, which is greater than 0. So let us try to recall the theorem. The limit comparison, since c is 1/2, we're going to have the first condition. So if the limit of u sub n over v sub n is equals to c, which is greater than 0, and now we have c, which is really greater than 0, then the two series either both converges or diverges. So let us now find out if both series diverges or converges. So let's try to look at our v sub n. So since the limit exists and the v sub n equals to 1 over n squared is what? A p series with p equals to 0, which is greater than 1. Then we all know that based on the p series definition of it, if the p series stated that the summation of 1 over n raised to the power of p ranges from 1 to infinity is convergent only if p is greater than 1. So as you can see here, our p is 2, which is greater than 1. No? So therefore, the series that we have, which is the summation of 1 over 2n squared minus 1 ranges from 1 to positive infinity, is a convergent by the part 1 of the limit comparison test. So let us take a look at our next example. Example number 4, which is we have also again to test the series for convergence or divergence using the limit comparison test. So for the solution, we have to really indicate what is the test that we are going to apply. No? So the test that we're going to apply for this one is the limit comparison test as indicated. No? So for this one, we're going to let the u sub n equals to 1 over n plus the square root of n, and v sub n equals 1 over n, which is the n is the dominant n in the denominator of our given series. Right after that, we apply the limit. The limit of u sub n over v sub n ranges from, as n approaches to positive infinity. Since we already have the v sub n and u sub n, we have to substitute what is our u sub n and v sub n to the limit as n approaches to positive infinity. So the limit of 1 over n plus the square root of n all over 1 over n ranges from, as n approaches to positive infinity. So right after that, we have to simplify this, or divide, but then to easily divide the both series, or the u sub both series, or the u sub n and v sub n, we have to multiply it, the numerator, to the reciprocal denominator, which is the n over 1. So the limit as n approaches to the positive infinity of 1 over n plus the square root of n multiplied to to n over 1. So we have now the limit of n over n square root of n. No? And so we have now to multiply the both numerator and the denominator for n over n, no? So what we have now is the limit of n over n over n plus 1 over square root of n. As you can see, n over n is equal to 1, no? So we need to simplify it. So the limit of 1 over 1 minus square root of n, yeah, ranges, as n approaches to positive infinity, then we have now the 1, evaluate the limit or apply the limit. So we have the 1 over 1 plus 1 over square root of infinity, which is 0. No, 1 over infinity is 0. So we have 1 over 1 minus 0, which is 1, which is greater than 0. So 1 is greater than 0. The limit comparison condition number 1 states that the limit of u sub n over v sub n as n approaches to positive infinity equals c, then the two series either both diverge or both converge. So applying this, no, this condition number 1, the limit of the series exists, no, and it's greater than 0, which is 1 greater than 0. It satisfies the first condition of the limit comparison test. Now, since the limit exists and the v sub n equals 1 over n is a harmonic series, so this harmonic series on positive terms is considered as a divergent series. So by the theorem of so therefore the series, which is the summation of 1 over n plus the square root of n, ranges from 1 to positive infinity, is also divergent by the first condition, no, of the limit comparison test. So I hope you learned something about the limit comparison test. So let us now proceed to our last topic, which is the integral test. So this integral test is let us apply the theory of improper integrals for this test. So what is that all about? So this theorem sometimes used to test an infinite series of positive terms, no, for convergence, is the integral test, which utilizes the theory of improper integrals. So what is that all about? So the integral test, we are going to let f of x be a function that is continuous, decreasing, and positive valued for all x greater than or equal to 1. Then the infinite series, which is the summation of our f of n, ranges from 1 to positive infinity, equals to f of 1 plus f of 2 plus f of 3 plus f of 4, so on and so forth, as it approaches to f of n, no, is convergent if the improper integral is the improper integral such that the integral of f of x from 1 to positive infinity dx, or with respect to x, exists, and if this divergent, if the limit of the integral of f of x dx from 1 to b equals to positive infinity. So to help us understand more about this integral test, or what is this one talking about, let us have two examples. So for the example, next example, we're going to apply the integral test for the convergence or divergence of the series. So we have the series, which is the summation of 1 over 3n plus 7 squared, the quantity of it, from 1 to positive infinity. So we have to indicate first for our solution what we're going to apply. So we're going to apply the integral test. So let the function f of x equals to 1 over 3n plus 7 squared is a continuous, positive, and decreasing on the closed interval 1 up to positive numbers. Yeah, positive infinite numbers. So we can apply the integral test. So what would be our integral? The integral of f of x dx from 1 to positive infinity equals to, what is our f of x? So we let the f of x as 1 over 3, quantity of 3n plus 7 squared dx, no? So we have now the integral of 1 over 3x plus 7, the quantity of 3x plus 7 squared dx from 1 to positive infinity. So we apply the theory of improper integrals, no? So the improper integrals for this one is equal to the limit of, the limit as we approaches to positive infinity of the integral of 1 over the quantity of 3x plus 7 squared from 1 to b dx. No? So, for this one, we're going to apply the u substitution. So, we're going to let u equals to 3x plus 7. So, what is the derivative of our u? The derivative of our u is 3 dx. So, equate this to find the dx. The dx that we're going to have is the du over 3. So after this one, we apply the u substitution. So it will be like the limit as we approaches to positive infinity of the integral of 1 over u squared multiplied to the du over 3 from 1 to b. So after this one, we take out the constant, no? And take out the constants, which is 1/3. So what we're going to have now is the limit of b approaches to positive infinity of 1/3 of the integral of u raised to the power of negative 2 from du from 1 to b. So after this one, we going to apply the integral or the integration. So the integration or the integral of u negative 1 equals to u negative 1 plus 1 over negative 2 plus 1. So what we have now is the limit of b as approaches to positive infinity of 1/3 multiplied to the integrated u negative 2, which is not yet done. No, negative u negative 2 plus 1 over negative 2 plus 1, evaluated from b to 1. No. So next is that we already have it, no? Simplify it. So we have the limit of 1/3, limit of b approaches to positive infinity of 1/3 from 1/3 of u negative 1 over negative 1 from b to 1, no? So after that one, let us still simplify it. So we can still simplify it. So the limit of b approaches to positive infinity of negative 3, which we also have negative 1, no? So we can have the negative 3. So 1 over u multiplied to 1 over u from b to 1. After that, we can now substitute back what we let earlier, which is the u equals to 3x plus 7. So right now, after substituting, we are going to have now the limit of the limit as b approaches to positive infinity of negative 1/3 times the 1 over 3x plus 7 from b to 1. No. After this one, let us evaluate the upper and lower bound of our integration earlier. So what we have now, this is the last problem, no? Here, nata. So we have the limit of b approaches positive infinity. To evaluate it, no, we have the negative 3 multiplied to the difference of two function, which is 1 over 3b plus 7 and 1 over 3 times 1 plus 7. So what we have right now is the limit as b approaches to positive infinity of negative 1/3 multiplied to the difference of 1 over 3b plus 7 and negative 10. Right after that, we can apply now the limit. So we apply the limit, negative 1/3 multiplied to the sum of 1 over 3 multiplied to infinity plus 7 minus 1 over 10. As you can see here, the 3 multiplied to infinity is 0. So 0, 3 multiplied to infinity is infinity plus 7 is infinity. So 1 over infinity is 0. Now, what we have right now is negative 3 multiplied to the difference of 0 minus 1/10 the answer that we have now is negative 1/3 multiplied to negative 1/10. The answer is 1/30. No, so for this problem, no, we need to conclude that the integral states that if the improper integral such that this integral of f of x dx from 1 to positive infinity exists. As you can see here, what we have earlier, the integral, no, exists, which is 1/30, no. The series is convergent. So since the improper integral of the given series exists, which is the limit as b approaches to positive infinity of the integral of b of the integral of 1 over the quantity of 3x plus 7 squared from 1 to b dx equals 1/30. No. Therefore, we can conclude that the series, which is the summation of 1/3, the quantity of 3n plus 7 squared from 1 to positive infinity, is convergent by applying the integral test. Let us proceed to our last example. So, what we're going to do is still apply the integral test for the convergence or divergence of the series. We have the summation of n squared all over n cubed plus 1 ranges from 1 to positive infinity. So, indicate first what we're going to apply. So, we apply the integral test. So, let the function be equal to f of x equals to x squared all over x cubed plus 1 is continuous, positive and decreasing on the interval, the closed interval 0 to positive, no, the open interval 0 to positive infinity. So we can apply the integral test. So right after that, no, we have the integral of f of x dx from 0 to positive infinity equals to, we have the f of x equals to x squared over x cubed plus 1, which is our f of x. So we have now is the integral of x squared all over x cubed plus 1 dx ranges from 0 to positive infinity. So we apply the theory of improper integrals. No? So this is the last problem that we have. So we have the limit as b approaches positive infinity of the integral of b the integral of x squared over x cubed plus 1 from 0 to b dx. So for this one, we're going to apply the u substitution. So we let u equals to 3x plus 1. Then the derivative of u, no, we have the 3x squared dx. So to equate, we have to have dx, we have du over 3x squared. No. So apply the u substitution. We have the limit as b approaches to positive infinity of the integral of x squared over u multiplied to du over 3x squared from 0 to b. So as you can see here that we have negative 2 from here and negative 2. So negative 2 over negative 2 is equal to 1. No? So what we're left here is the limit of the limit as b approaches to positive infinity of 1/3 of the integral of 1 over u du. No? From because we have, the reason why we have 1/3 here is that we have to take out the constant, which is from this part we have 1 over 3x squared. So we have to, the x squared over x squared is 1. Then we still have the 1/3 u. So we can factor out the constant instead to make it easier. So the integral of 1 over u is natural log of u. No? So it is now equal to the limit as b approaches to positive infinity of 1/3 multiplied to natural log of u from b to 0. So we have to evaluate the upper bound and the lower bound of the integration. To do this one, you have to minus the upper bound to the lower bound, if you still remember. No? So this is the last problem that we have, the last equation. So let's continue. No, but before anything that, no, we have to substitute back first, no? No, I'm so sorry. The u equals to x cubed plus 1. No. So what we have now is the limit as b approaches to 1/3 of multiplied to the limit of 3x squared plus 1 as b, from b to 0. So for this one, we apply or evaluate the upper bound and lower bound. Now we have the so the limit as b approaches to positive infinity of 1/3 multiplied to the difference of ln b cube plus 1 minus the ln 0 plus 1. So for this one, we can substitute or apply the limit as b approaches to positive infinity. So we have now the 1/3 multiplied to the difference of ln infinity cube plus 1 minus ln 0 plus 1. So for this one, let's simplify now. This is the last step that we had. So what we have right now is that ln 0 plus 1 is negative infinity. So negative infinity plus 1 is still negative infinity. Now, so 1/3 infinity minus negative infinity is that we have the infinity. So 1/3 multiplied to infinity, which is a constant multiplied to infinity, is still infinity. So for this one, we can conclude, or we can state that the integral test states that if the proper integral of f of x dx from 1 to positive infinity equals to infinity, the series is divergent. Since the proper integral of the given series is divergent, exists at divergent, so the limit as b approaches to positive infinity of the integral of x squared over x cubed plus 1 from 0 to b equals to infinity. Therefore, we can conclude that the series, which is the summation of n squared over n cubed plus 1, ranges from 1 to positive infinity, is divergent by applying the integral test. Now, let us test your knowledge about this topic. Let us have exercises. So these exercises has 3 parts. These exercises have 3 parts, which are part A, part B, and part C. So let's have this one. Letter B. Letter A, determine whether the series converge or diverge by applying the comparison test. Then letter B, determine whether the series is convergent by applying the limit comparison test. So letter C, and lastly, the last test, determine whether the series is convergent or divergent by applying the integral test. So, I think that would be also it. This is me, Marie Isabel Emma Yorca, a third-year student from the Bachelor of Secondary Education major in Mathematics at the University of Southeastern Philippines. Would like to thank you all for listening, and may God bless us all.